In this video, we'll see how we can calculate the reorder point given a desired cycle service level. Previously, we said that reorder point is equal to the average demand during lead time. It was for the case when we had no uncertainty in the demand or lead time. But here we'll assume that there is some uncertainty in the demand. For the time being, we'll assume lead time is fixed. Let's see how the demand can materialize during lead time. Here we have three scenarios. In the first scenario, the demand during lead time is less than the reorder point or the average demand during lead time. So we have no shortage at the end of this cycle. In the second scenario, the materialized demand during lead time is more than the average demand during lead time. So we have some shortages at the end of the cycle. In the next scenario that is shown with this red curve, the materialized demand is even higher. So the number of shortages is also higher at the end of the cycle. So here we can see there is a high chance, if we consider the reorder point to be equal to the average demand during lead time, so the probability of having shortages at the end of the cycle is high. In order to avoid this high probability and in order to satisfy a desired cycle service level, we will add some safety stocks to our reorder point. So our reorder point will be the average demand during lead time plus some safety stock. The same system, same scenarios, but this time with some safety stock. So here this amount is safety stock, and then we have this amount which is the average demand during lead time. In the first scenario, of course, we didn't have any shortages. We will not have any shortages with this. In this case, when we have added the safety stock to the reorder point. In the second scenario here, we can see again we do not have any shortages, and it is this time the safety stock that protects our system from ending up with some shortages. And if the demand is really higher than the average demand during lead time, then we'll have some shortage here at the end of the cycle. So in this case, the probability of having shortages is reduced by adding some safety stock. Now let's see how the safety stock can be calculated. We'll start with notations. D is the stochastic variable for demand per unit time. Then we have d bar and sigma d as the average demand and the standard deviation of demand per time unit. And then we have L as the stochastic variable for lead time. We defined L bar and sigma L as the average lead time and standard deviation of lead time. And then we can calculate, if we define DL as the stochastic variable for demand during lead time, then we can calculate its mean, which is mu DL, and standard deviation, which is denoted by sigma DL, under the assumption that the demands in different time units are independent of each other. You can also see some examples or explanations about how the stochastic variables can be aggregated at the end of this slides in the appendices. So the average demand during lead time is calculated as the average demand per time unit multiplied by the average lead time, and the standard deviation of demand during lead time is simply calculated using this formula, which is dependent on the average demand, variance of average lead time, variance of the demand per time unit, the average demand to the power of 2, and the square root and the variance of the lead time. Yes. The important point in these formulas is that the time unit that is used for the D, for the demand per time unit, should be consistent with the time unit used for L. In other words, if you are working with the demand per year, then you need also to convert your lead time to years. Or if you have your lead times in weeks, for example, and if you want to work with weeks, then you need to calculate the weekly demand from maybe a given yearly demand, right? So make sure that the times are consistent for the demand and for the lead time. Then you can use these formulas for your calculations. And it is just what we saw in the other slide. If we set the reorder point equal to the average demand during lead time, then there is a high chance of having stockouts at the end of the cycle. But if we add this the safety stock to our reorder point, then the risk of stockout or the risk of shortages will be reduced. And then we'll see how we can calculate this SS, the safety stock. Let's assume that we have S1 as a given cycle service level. We want to find a value for ROP for which the probability of demand during lead time being less than ROP, or in other words, the probability of having no stock out, is at least equal to S1. In order to be able to solve this equation, we will consider the equality portion of this inequality. So we want to find the smallest ROP that holds in this equation. So we have a distribution of demand during lead time, we have a desired service level, and we want to calculate ROP. Moreover, we will assume that DL, the demand during lead time, is normally distributed with mean mu DL and the standard deviation sigma DL. So the left hand side, the probability of having no shortages at the end of the cycle, can be written as, you can see here, this expression. So we will subtract the mu dl from both sides and then divide both sides by sigma dl, right? So we'll get this probability. And this probability here, of course, it should be less than and equal to, so you need to add this equality here. Then the dl minus mu dl divided by sigma dl is in fact a random variable that is distributed according to a normal distribution. So this expression can be written as probability of n, which is a standard normal distribution, which follows a standard normal distribution being less than ROP minus mu dl divided by sigma l. And we want to find a ROP that makes this probability to be equal to S1. If we define Z as the Z-score corresponding to the service level S1, so if we have the S1, then the Z-score from a standard normal distribution can be easily calculated, and let's S denote this Z-score. Then we know that Z is equal to ROP minus mu dl divided by sigma l. Z is calculated from S1. We know mu dl, we know sigma dl. In order to find this ROP, which is the only unknown in this equation, we need to solve this equation for ROP, which will give us ROP is equal to mu dl, average demand during lead time, plus Z, which is the Z-score corresponding to the service level S1 multiplied by the standard deviation of demand during lead time. And this Z is in fact the number of standard deviations above the average demand during lead time. And this value, when calculated, should be rounded up to hit at least the service level required in the system. Here we have a new notation C, which is the expected number of cycles with shortage per year. Let's see how it is calculated and how it is related to S1, which is the cycle service level. S1 is in fact the fraction of the cycles without any shortage, right? So 1 minus S1 is the fraction of cycles with shortage. And if you remember from the economic order quantity model, D over Q was the expected number of cycles per year. So if we multiply the expected number of cycles per year by the fraction of the cycles with shortage, then we will get the expected number of cycles with shortage per year. And then if we solve this equation for S1, so we can see S1 is equal to 1 minus CQ over D. We'll see some examples in which we need to use this formula to do our calculations.